This is the 8th lecture and problem session, second problem session. We work out problems on FET and BJT characteristics and also a few problems on biasing. The first problem that we take is that of an FET, a JFET with a 10 volt supply, a 5K resistance, a JFET, N channel, and there is no other connection. There is a V in here, plus minus. This is the circuit and V out is here. It is given that JFET has IDSS, the drain saturation current, as 2 milliampere. The pinch of voltage is minus 3 volt, and what you are asked for is to sketch a set of characteristic curves. And I will tell you systematically how to do it. And on these plot a load line. The load is given, so the load is given, power supply is given, load line can also be drawn. Then you are required to find out the values of V in, range of V in, required to obtain operation in this saturation region for saturation. This is the question. This is the circuit. IDSS and VP are given. You have to draw a set of characteristic curves. You have to draw a load line. And you are required to find out the range of input voltage V in for saturation. Note that V in is the same as VGS. Okay. So basically it is required to find out the range of VGS for saturation to occur. Now the first thing we do is write down the characteristic. The characteristic is, since all quantities are DC, let us confine to DC, I sub D is equal to IDSS 1 minus VGS divided by VP whole squared, provided VDS is greater than VGS minus VP, provided this is true. Okay. In our case, I sub D is equal to 2 milliamperes multiplied by 1 plus VGS by 3 whole squared, so many milliamps, because 2 is in milliamps. To draw a set of characteristics, what we do is we take this and find out the values for several values of VGS. For example, VGS equal to 0 will make ID equal to 2 milliamperes. Okay. I have calculated for several values. For minus 0.3, just a figure, if VGS is minus 0.3, you calculate this, it calculates out to 1.62, approximate figures. If VGS is minus 0.5, it calculates to approximately 1.4, minus 1, 0.9, and minus 2 is 0.22, minus 3, how much? 0. Okay. These are good enough for calculation, for drawing the characteristics. Okay. Now the characteristics we draw like this. I sub D, in the characteristics we show the total voltage and total current. Okay. Now if VGS is 0, the current saturates at 2 milliamperes. So at 2 milliampere you draw a line. At 2 milliampere you draw a line, but you know this line is true for VGS equal to 0. The line cannot start at VDS equal to 0, because for saturation VDS is to be greater than VGS minus VP. Okay. So VDS in this case the saturation line is VDS greater than VGS minus VP. So VDS must be greater than or equal to 3. So on this line you find out the point at which the voltage is 3 and draw a vertical line. So the saturation will start here, alright. Saturation will start here. This part of the characteristic we shall have to draw ourselves. We will see how to draw this. Let us take the next point, let us say minus 1, okay. At minus 1 the current is at 0.9. If this is 1 and this is 0.9, this is VGS equal to minus 1 and this is 0.9 milliampere, alright. Now where does saturation start? If VGS is minus 1, obviously it starts at 2, okay. So you draw a vertical line at 2, this is the point at which it starts saturating, alright. Then let us take VGS equal to minus 2, the current is only 0.22. So we can draw safely from here because it will extend up to, from which voltage shall it start saturating? 1 volt, and therefore from here it shall be a straight line, VGS equal to minus 2. So this is the locus of the saturation line, okay. This is the locus of the saturation line, the red line. This is the line which describes VGS equal to VGS minus VP. Is that clear? Okay. The rest of it I could draw the other two also, minus 0.3 and minus 0.5, but I am showing only 3 of them. I will show the total picture later and I will tell you why I calculated minus 0.3 and minus 0.5. Later calculations will justify why this was necessary, but what remains is to draw the rest of the characteristics, okay. The rest of the characteristics, you know that between VDS equal to 0 and VP it is a ohmic characteristic, so you can approximate it by a straight line, alright. So our characteristic would be like this, this is one, this is the other, and this is the third. You can approximate that by a straight line because it is ohmic, ID versus VDS. Reasoning for drawing the straight lines, because before pinch off increase of VDS should cause an increase of ID approximately linearly, because it is ohmic region. Actually it is not, because there is a change in the width of the depletion layer. Actually it is not, so it would be rounded off, but this region is so small, and since we are not operating in this region either, we will operate only in the saturation region that is beyond this red curve, and therefore this part is of least interest to us. We can approximate it by a straight line or a freehand line, okay, that is good enough. Now the total characteristic I will now show which I drew to scale, looks like this, looks like this. Now you can see, let me take this out, you can see here VGS equal to minus 0.3 and minus 0.5 also, okay. We approximated not by a straight line but by a rounded off, because nothing in this world is has a sharp corner. Nature abhors sharp corners. So if it is a straight line and then a straight line, there is a sharp corner. So they are all rounded off because it is not exactly ohmic, and saturation, onset of saturation is not very sharp either, okay. Anyway, I have shown minus 0.3, minus 0.5 in addition to 0, minus 1 and minus 2, and obviously this line would be VGS equal to VP, that is minus 3 volt, by this or minus 3. The next part of the question says that on this plot a load line. Well, load line, the characteristic would be VDS, the load line would satisfy VDS equal to VDD, which is 10 volt, minus RD, there is no resistance in the source terminal, so it is RD, which is 5K multiplied by ID. This is the load line. and you see that ID equal to 0 leads to VDS equal to 10 volt, and VDS equal to 0 leads to ID equal to 2 milliamps.
Sir?
Yes.
In this case, while using the total ID and the total VDS, shouldn't it just be the DC parts?
Yes, since we are considering the DC circuit, only the DC circuit, we are not considering the presence of a signal. We use the capital letter symbols, but you can use the small letters also with the total. But the total is simply DC, there is no AC. In other words, here VDS, small VDS is equal to capital V. Okay, but when you draw the characteristics, you must show the total voltage, total current. Okay, because DC as well as AC must be governed by these characteristics. Okay, so the load line, therefore, there are 2 points. These are enough. One is 10 volt 0 milliampere, and the other is 0 volt 2 milliampere. These are the 2 points. This is one and this is the other, so you draw the line. And the Q point should be somewhere here, maybe VGS equal to -1 is a good Q point. Alright, this point is a good Q point. And you also see that what the last part of the question, what values of V in are required to obtain operation in the saturation region. You see, the operation must be on this load line. So on this load line, you should not go into the ohmic region, you should remain in the saturation region. This is why I drew that VGS equal to -0.5. This is approximately -0.5, and therefore the range of V in is -0.5. VGS must be less than -0.5. If it is greater, then it goes into the ohmic region, and it must be greater than -3 volt, right? So this is the range of operation between VGS equal to -0.5 and -3, and VGS is exactly equal to V in, because there is no resistance at the source terminal, and that completes the question.
So this is the graphical method for determining the range.
That's correct. It asked for, no, otherwise you have to argue it out. The load line, where does it intersect a saturation characteristic? So you can do it analytically also, that's no problem. Okay, the next question is question number 4 in the tutorial sheet, and this question is like this. Again we have an N channel JFET with a resistance at the drain and a resistance at the source terminal R sigma. Then there are 2 resistances, R1 and R2, supplying the gate, and what is given here is, this is of course VDD plus VDD. What is given is VDD equal to 20 volts. 20 volts. VP is given as -5 volt, and IDSS, the drain saturation current, is given as 10 milliamperes. Okay, what you want is design this circuit. You are asked to design this circuit such that ID, the drain current, is 5 milliamperes. Design for ID equal to 5 milliamperes, and VDS is equal to 10 volt. This is the design specs. Design specs are shown in this color. And then you have to illustrate your answer by sketching a load line on a set of ID versus VDS characteristic. Okay, so characteristics are needed and load line are needed. This is the condition of the problem. Okay, it's a design problem. Your operating point is specified. You are not choosing the operating point. It's specified as 5 milliampere and 10 volt. What should be these resistances? RD, R sigma, R1, R2. Okay, this is the design problem. Now obviously, since there are only 2 specs and 4 unknowns, 2 of them can be determined at will, not quite at will, as we shall see. You cannot choose, for example, RD equal to 5 meg. No. Can you? Why not?
It will exceed 20.
It will exceed the source voltage, the VDD. So it's not at sweet will. There are constraints. Let us see what these constraints are. But our relationship for I sub D and VGS is 10 multiplied by 1 plus VGS. I am using the total because someone objected. Okay, it's a DC design. I could use the capital also, but doesn't matter. VGS by 5 whole squared, so many milliamperes. All right, and what I want is that ID should be equal to 5 milliampere. Therefore, this should be equal to 5 milliampere, which gives me a solution for VGS. VGS should have two values, isn't it? Why? This is square. So it should be two negative values, and the values, if you solve for this numerically, minus 1.46 is one value, this is my answer, and minus 8.5. Now 8.5 obviously is not permitted because it is greater in numerical value than the pinch off voltage. It is less than Vp, and therefore acceptable value is minus 1.46. Agreed? Under this condition, that is VGS equal to minus 1.46 and VDS equal to 10 volt, what is VGS minus Vp? That is equal to 3.54. Isn't that right? VGS minus Vp, so 5 minus 1.46, that is 3.54. And in this VDS is greater than this quantity, therefore the transistor is in the saturation region. So Q is in saturation. This must be verified, otherwise this relationship shall not be valid. Okay, this is valid only in the saturation region. So Q is in saturation. Okay. The next question is how to design this circuit. We have found out a VGS. Now VGS obviously is 20 R2 divided by R1 plus R2. If you refer to the circuit, this is VGG minus the drop in the source resistance, that is R sigma, which is equal to I sub D. Now what is I sub D? 5 milliampere, this is the specification, multiplied by R sigma, that should be equal to minus 1.46. All right, this is VGS, this is VGG, and this is VS. This is VG, I'm sorry, this is VG and this is VS. All right, because the gate does not take any current. Is this equation clear?
Yes, sir.
What is the second equation? Second equation is 20 minus the drop in RD and RS. So it is ID, which is 5 milliampere, multiplied by RD plus R sigma. This should be equal to 10. All right, these are the two equations that we have, from which we have to decide what our RD and R sigma, R1 and R2 should be. Agreed? Now one of the things that we can do is, since our gate is being supplied through a resistance combination, okay, R1 and R2, or is it the other way around? No, it's okay. Suppose we make, since we have a choice, suppose we make R1 go to infinity. Can we do that? We can do that because the gate does not take any current. Let's take R1 as infinity. If R1 is infinity, then what is VGS? VGS is simply minus the drop in this resistance. Isn't that right? VG would be 0, Vs would be a positive quantity. So VGS would be 0 minus a positive quantity, in other words a negative quantity. So if I have this choice, why don't I make it? If I do that, if R1 goes to infinity, then you see R2 is arbitrary because this quantity drops down to 0, and R2 can be any large value. Let's say R2 is 1 meg. It is arbitrary now. It does not affect the equations. Yes.
R2 is arbitrary, then we can as well leave that terminal as open circuit also.
Yes, there is a question there. Is the question clear? If R2 is arbitrary, why don't you leave it open? Why use another resistance?
Then G would be a floating point.
Correct. So what?
So VGS has to have some specified value like greater than VP, which
That's
cannot be.
That's
Which
right.
cannot be.
If it is floating, there is another danger. I am glad you asked the question. The danger is that if this terminal is left floating, it accumulates charge, static charge from the atmosphere. Suppose it's a very dry atmosphere, then there is static charge in the atmosphere. It accumulates charge, and VGS may be such that the operation goes into a different region. Also, then VGS will not be controlled. So what we want is, we must provide a path for any charge that tends to accumulate to go to ground. That's why we must use a resistance.
So why do we take a high value for the resistance?
We can take a low value also. Only problem is, if we connect, after all it's going to be used for signals. So if we connect a source here with a source resistance Rs, this resistance must be large compared to Rs. Okay, so use as high a value as possible, so that we can use this circuit with a high resistance signal source. Signal source resistance, even if it is 10K, this is 1 meg. Oh, good enough. Okay, that's why you use a high resistance. Any other question? Now, as soon as we have done that, that is, we have chosen R1 equal to infinity, R2 is arbitrary 1 meg, then this part of the equation drops out, and we have these two clean equations from which we can find out R sigma and RD. The calculation, my calculation gives R sigma as equal to 293 ohms and RD as 1.707 K. 1.707. The sum of the two, as you can see, is 2K. The sum of the two is 2K. RD plus R sigma. It has to be so. Why not? Why? Because it is 20 minus 5 milliampere, sum of these two equal to 10. So this must be 2K. Okay. Now the later part of the question says, illustrate your answer by sketching a load line on a set of ID versus VD characteristic. So we go back to this relationship, ID equal to 10, 1 plus VGS divided by 5 whole squared milliampere. And we draw a set of characteristics. Let's say VGS equal to 0, then ID is 10 milliamperes, VGS equal to minus 1, 6.4, minus 2, 3.6. We can go ahead and go up to minus 5. We don't go beyond that. Okay. So then we can draw a set of characteristics by arguing VDS I sub D. This is 10 milliampere, so this is VGS equal to 0 volt, and the saturation would now be at plus 5. Okay. So the other set of characteristics, well, we can for the others we can find out the saturation point. It would go like this, and therefore the other set of characteristics, VGS equal to minus 1 gives 6.4, so it's slightly higher than half, it's somewhere here, minus 1 and minus 2 gives 3.6, so it's somewhere here, minus 2 and so on which if you want to draw a load line, the load line where does it start here at 20 volt? Let's take 7, okay, this is 20 volt, and where does it start here? Pardon me? Where does it end here on the ID characteristic?
10 million.
10 million.
10 million. Okay. So this is my load line. Oh, I'm sorry, it didn't become a straight line. Anyway, you make it a straight line. It touches at 20 volt, and you now see that VGS cannot be 0. It must be restricted to a value, whatever this characteristic was, between this value and minus 5. Whatever this value is, you can do that graphically or analytically, I don't care. Okay. What is the slope of this line? Minus 1 by RD plus R sigma. The next question is question number 6 in the tutorial sheet. Yes? Okay. Question 6 says you have a 15 volt source, and for a change we consider an enhancement mode FET. There are two resistances, R1 and R2. This is an E MOSFET. So VT, threshold voltage, it requires a positive threshold voltage, and the circuit is, there is a resistance here, sorry, this is a 4K resistance, and there is a 4K resistance here, and this comes to this point and goes to ground. This is the circuit in which it is given that I sub D is equal to 3 times VGS minus 2 whole squared milliampere, which means that VT is equal to plus 2 volts. Okay. This is what is given. It is also given that R1 plus R2 is equal to 100K. These are the two things that are given. That is K for NMOS FET. You know the constant is given as K. K is 3 milliamperes. Is that correct? No. K is
3 milliamperes
per volt squared. You must make the dimension correct. 3 milliampere per volt squared, and VT is given as 2. Now the questions are, firstly, that you have to find out I sub D when R1 is equal to R2. You are required to find out the drain current when R1 is equal to R2, and then you are required to find out R1 and R2 for the transistor to operate at the edge of saturation. Edge of saturation. And third is find R1 and R2 for maximum power dissipation in the transistor. Maximum power dissipation in Q. These are the 3 parts of the question. Let's look at these parts one by one. Okay, now we'll get some complication. Let us see what these complications are. Now if R1 is equal to R2, then you see that VGS is equal to 7.5 minus
4ID.
8k, not 4, 4k plus 4k, 8k multiplied by ID, okay, where ID is in milliamps, alright. And the other equation is that ID that is
So there should be 4K.
quite correct. It is only R sigma. It is only R sigma. Okay. And the other equation is that ID equal to 3, then VGS minus 2. Pardon me? VGS minus 2. But VGS is 7.5 minus 4 ID. So it would be 5.5 minus, yes, 4 ID square. How does this come? Because our VGS minus 2 and VGS is 7.5 minus 4 ID. So 7.5 minus 2 is 5.5. Is the point clear? Okay. So this is a quadratic equation which we shall have to solve. And the quadratic equation solution, my solution is that I sub d is equal to 1.22 milliampere. The other solution is not acceptable. You have to find out why. And if ID is this, then obviously VGS is equal to, substitute this ID here, find out VGS, this comes as 2.6 volt, and VDS, which is now 15 minus 8k multiplied by 1.22 milliamps, and this comes out as 5.24 volt. Alright, this is the first part of the question. If R1 is equal to R2, this is the operating point, that is 1.22 milliampere and 5.24 volt at VGS equal to 2.6 volt. VGS now is required to be greater than VT, okay, the threshold voltage, and VT was 2 volts. So 2.6 is an acceptable value. Okay. Second part of the question, if the transistor operates at the edge of saturation, the condition is that VDS should be equal to VGS minus 2. This is the condition. And now what is VDS? 15 minus 8 ID. Agreed? ID in milliamperes. VDS is equal to 15 volt, VDD minus 4K, and the current is ID. This should be equal to, what is VGS now? 15 R2 by R1 plus R2 minus 2 minus
4ID.
4.
Minus 4ID.
That's right. Now you see what is ID? ID is VGS minus 2 whole squared multiplied by 3. Agreed? 3 times VGS minus 2 whole squared. But VGS minus 2 is this. You have to proceed very cautiously here because you might get lost. Let's call this right hand side as equal to x. Okay, then x is VGS minus 2. Obviously, this is what I have written. Therefore, I can write this as 3 times x squared. Okay. Substitute this. You have to go back and forth. Substitute this here. Then you get the equation 15 minus 24x squared is equal to x. Solve for x. My solution is that x is approximately equal to, the acceptable value is half of square root of 1441. I am leaving this algebra to you. And if you can find out x, then you know ID. Okay, ID is 3x squared, so it would be 3 by 4 multiplied by 1441. So many milliamperes. And if you know ID, then too large a value?
This is the order of an ampere.
Is that permitted?
No, sir.
No, so
Or I have made a mistake?
Too large.
Okay, I have made a mistake. This should be, yeah, this is divided by, please do correct this. I was waiting for this. This is, I have made a mistake here. This should come as 48. So instead of 2, it should, instead of 4, it should come as 48 squared. Will that be reasonable now? Yes, that would be reasonable. Okay.
So can you explain the solution again?
Which solution?
You used x in the right hand side.
Oh, you see, it's a, what I do is, I have to find out ID. ID is 3 times VGS minus 2 whole squared. And VGS minus 2 can be written in terms of ID. So this right hand side I put as x, so it becomes 3x squared. Okay, and I substitute this back here, so I get a quadratic equation, and this is the solution. Once we know ID, what else is to be found out? R1 and R2. Okay, if I know ID, then I know R2 by R1 plus R2, and R1 plus R2 is given as 100K, and therefore I can find out R1 and R2. My my solutions I have not worked out. So you do that yourself. Any question on this? It's slightly involved, but you have to keep track. You have to keep track. Now the third part of the question. Third part of the question says, find R1 and R2 for maximum power dissipation. Now maximum power dissipation, let us find out what is VDS. VDS is 15 minus 8K multiplied by I sub D, the DC VDS, and therefore PD, the power dissipation in the transistor, the gate does not take any current, so the power dissipation will be only due to the drain current. So it would be 15 minus 8 I sub D multiplied by I sub D, where I sub D is in milliamperes. And you want this power dissipation to be maximum, so you put dPd dId as equal to 0. Obviously the second differential coefficient is less than 0, negative, so that's a condition for maximum, right? Okay, this gives me I sub D as equal to 0.94 milliampere. So this would be 15 minus 16 ID, isn't that right? Equal to 0. So ID equal to 15 by 16, which is 0.94 milliampere. And if it is 0.94 milliampere, then 0.94 should be equal to 3 times what? VGS minus 2 whole squared. So you know VGS. From this you know VGS, and VGS comes out as 2.56 volt. If you know VGS, then of course you know R1 and R2. Okay, let's see. 2.56 would be equal to 15 power supply multiplied by R2 by R1 plus R2, then minus 4 ID, and ID is known, ID is 0.94. Therefore you know R2 by R1 plus R2, and you know R1 plus R2 is 100K, so you can find out R1 as well as R2. My solutions here, it was simpler to work out, so I did 42K, and R1 is equal to 58K. That's the solution. Any question on this? Yes.
So for the power dissipation,
Yes.
we will consider only the drain source voltage.
That's right, because the gate does not take any current. The transistor takes current only at one terminal, that is at the drain current. So, drain current multiplied by the voltage across the drain source. Okay. The next question, question 9 in the tutorial sheet, is that of a BJT. BJT biased like this, 220 ohms, 12 volt plus 12 volt, 820 ohms. There is a capacitor which goes to another load 2.2 K, which as you will see will not be of interest at this point. The biasing is done through 60 K and 30 K. Of course, there is a capacitor here through which the signal source is connected. This is the input Vs and this is the output across the load. The question is, compare the operating points for beta equal to 100 and call this Q1 operating point, and second operating point for beta equal to 300. Compare the two operating points and then answer the question whether the circuit is adequately stabilized for beta variations or not. All right. So, the procedure is straightforward. Our VBB is simply 12 volt multiplied by 30 K divided by 30 K plus 60 K. So, this is equal to 4 volts. Fine. This is VBB. We have to find, and what is RB? RB is 60 parallel 30, 20 K. Okay. So, my equation is that 4 volt VBB should be equal to 20 K multiplied by IB plus VBE, which is 0.7, plus 220 ohm multiplied by beta plus 1. Let us keep it in terms of beta because we have to compare. Beta plus 1 multiplied by I sub B, which gives me IB as equal to 3.3 divided by 4 minus 0.7 divided by 20 times 10 to the 3, okay, 20 K plus 220 multiplied by beta plus 1, so many unit amperes now, because I have converted kilo to ordinary ohms. Now, if let me recollect this, IB is 3.3 divided by 20 plus 0.22 beta plus 1, so many millions. Okay. You must get into these conversions very quickly. So, a beta equal to 100, that leads to I sub B. If you substitute this, I hope I am right, it comes out as 78 microampere, and therefore I sub C is equal to, yes.
So we have derived the condition that beta RE should be much greater than RB for stability of beta, for stability of Q point due to variations in beta.
That's right.
So why don't we directly use this condition?
Beta RE
Should be much greater than RB.
RB, okay. So, RE here is 0.22 K and RB is 20K. So if it is 100, if beta is 100, then you get 22, which is not very large compared to 20. Alright. If it is 300,
So even that is not that much large.
why not? 60, not much greater. So Q point is not adequately stabilized. But you will see something more interesting if we work it out completely. This is a condition, beta RE must be much greater than RB, but you will see something more interesting that occurs here. Pardon me? No, for a stable operating point. The operating point is not stable here. You see, but you cannot do it, you cannot make quantitative assessment of how unstable it is. Okay? Quantitative assessment will be done only if we calculate the total thing. Let's do that. I sub C, if beta is 100, then it would be how much? 7.8 milliampere, and VCE would be 15, not 15, 12 minus I sub C R sub C, which is 7.8 milliamperes multiplied by 7.8 into 0.82 minus 7.8 7.878. Can you see why?
Yes.
Because IB plus IC. This multiplied by 0.22, and this comes out as 3.9 volt. That's perfectly all right. It's not a very bad operating point. Only thing is it may not be stable. It may not be stable. Let's see what happens when beta is equal to 300. If we proceed with the same formula, my calculations give I sub B as equal to 38 microampere, I sub C equal to 11.4 milliampere, and alas, VCE comes out as small as only 0.2 volt, which means that the transistor is driven into saturation region. BJT we don't want saturation. FET we always want saturation. Alright, you must remember this. Therefore, we argue that it is not stabilized against the variations in beta. The next problem that we take, any question on this problem? The next problem is one that we left in the main class unanswered. That is, we have a transistor which is biased like this, R sub C, a BJT in which the emitter is grounded, and I told you that we use a feedback from the collector to the base. Let's call this resistance as RB. The question is, for this circuit, derive an expression for delta IC divided by IC1 as a function of delta beta, that is due to beta variations only, assuming that delta VBE and delta ICBO they tend to 0. That is, these are held constant, only beta varies, which means that we are replacing the transistor. Okay, you are replacing the transistor by another one. To determine delta IC by IC1, what you do is you write the equation for VCC. If this current is I sub C and this current is I sub B, now you can't make all those things IC equal to beta IB and things like that, because ICBO comes into the picture. We will neglect it at the end, but let us see the general expression. General expression would be VCC would be equal to I sub B R, no, I beg your pardon, I sub B plus I sub C times R sub C, okay, plus VCE. Now this doesn't give me anything, I don't know what is VCE. So I don't go through this route at all. I go through this route, then I know. Okay, so it is plus IB RB plus VBE. Now I must bring ICBO. You also know that I sub C is beta I sub B plus beta plus 1 ICBO. So if I substitute this in this expression, then I get VCC as equal to beta plus 1, very interesting, IB plus ICBO. Do you see why?
Yes.
Okay. Beta plus 1 IB plus ICBO plus times RC plus RB IB plus VBE. And in addition, you know IB is equal to, after all you are trying to find an expression for IC, right? IB is equal to I sub C minus 1 plus beta ICBO divided by beta. Combine 1 and 2 to get an expression for I sub C. Alright? Have I gone too fast on this?
Yes, sir.
Oh, I did. Well, I did. What I did was, I didn't write a KVL around this loop. I wrote a KVL like this. Alright? And in this I substituted I sub C equal to beta IB plus beta plus 1 ICBO. That's what I did. Beta IB plus beta plus 1 ICBO. Then the expression becomes this. Interesting expression, because beta plus 1 comes as a factor of IB as well as ICBO. But my purpose is not IB. My purpose is to find I sub C. So this IB must be replaced, this IB and this IB must be replaced by this expression. Then after a bit of algebra, I hope my algebra is correct, I sub C comes as beta VCC minus VBE plus 1 plus beta RB plus RC times ICBO divided by RB plus RC 1 plus beta. The rest of the exercise is very similar to what we did for the other case. That is, what we will do first is, since we are concerned only with variations of beta, the first thing we will do is we will replace beta plus 1 by beta. Okay? This will replace by beta, this will replace by beta. And next we will play a trick, we will ignore this term as compared to these two. So my I sub C would be beta VCC minus VBE divided by RB plus beta RC. Then what I will do is I will take IC2 for beta 2, then I will take IC1 for beta 1, divide by IC1, and IC2 minus IC1, and that expression in my calculation comes as delta beta by beta 1 RB divided by RB plus beta 2 RC. This is the final expression. Okay. In the next problem session, we will work out problems on current mirrors and some more on BJT bias.